Hi, Victoria. Can you hear me?
Yes, I can hear you.
Thanks, Victoria. Did anybody tell you you're in a class by yourself? Because you are. You're the only one here. That was a joke. I was trying to be funny. It's okay.
That was funny. You got me.
All right, it's 10 o'clock. We'll get started. Victoria, did you have any questions about Module 9?
No, I don't.
Okay. I'm going to say this for the benefit of anybody who's watching this as a recording, that last week I put up a Zoom session where I went through Module 9. So if you need any help with that, well, obviously you can contact me as well, but I did go through it. You can watch my session that I did last week on Module 9. So for today, what I'm going to do is go through the test. I'll go through test 3.
All right.
Unless there's something else you want to see, Victoria. Is there anything else you want to see aside from the test?
No, not that I can think of.
Okay, fair enough. So this is practice test 3, and as it was with all the other ones, there's going to be, whoops, wrong, that's the wrong quiz here. All right, hang on. Let me get out of here. Let me get back to, hit the wrong quiz here. Let's go back. Practice test 3, there we go. The test will be pretty much exactly the same as what you're seeing here. Just do it again and again and again. And remember, you can get some extra credit by doing this practice test, getting 80% and taking that quiz that I just accidentally showed you. The other thing is that you're required to use the on-a-lock calculator, and my recommendation would be that you can right-click on it and open it in a new window, and then you can practice with it in the window adjacent to the test. That's how I would manage it. It's not going to be exactly the same on the test. There's another button that you press in the on-a-lock system that allows you to bring up the calculator. But this sort of allows you to emulate that situation. So you can see that you will have a periodic table. So I'm going to start off by going through the questions here, and the first 4 questions have to do with Module 7. And I'm going to go through and just do the problems. I might not go through and get the answers, but I'll certainly go through and show you how we do it. Victoria, you're the only one here. If you have to go at any point, don't feel bad. I'll continue on and do it for the benefit of anybody who's watching this as a recording later. I don't want you to feel obligated to stay just because you're the only one here. Okay. 4.00 times 10 to the 25th molecules. CR2O3. Now you can see it's going to be one step. I'm just going to put it down here. We know what the units are going to be on the bottom. It's going to be molecules of CR2O3. And on top, we're looking for moles. So we do actually have a relationship that allows us to go from, actually it's mole, I think is the mole CR2O3, I think is the correct. And you can see it says here how to express it, moles of Cr2O3 MOL. And the relationship here is 1 mole and then 6.022 times 10 to the 23 moles. Now let me go through and show you how you would put this into the on-a-lot calculator. And what you would do is you go 4.00, whoops, let's clear that out, try that again. 4.00, and then EE. And you can see what happens is it goes a darker gray color. That's kind of means that it's been activated. And then I'll hit 25. And then this is on the bottom, the 6.022 times 10 to the 23. So I'm going to go divided by 6.022 EE 23, and then hit equals. And there you go, that would be the answer. Now it would be to 3 significant figures because 4.00 has 3 significant figures as well. So the answer would be 66.4 moles of Cr2O3. Then of course you would fill in the blanks accordingly. Any questions so far?
No questions.
The mass of one atom of Ga we know it's going to be atoms of Ga on the bottom, and we're looking for the mass, so it's going to be grams of Ga on top. Now, if you look at the relationships we're given in the problem, we can see that grams, which would be the molecular weight here, is going to equal this number of atoms, 6.022 times 10 to the 23. So I put in the molecular weight I'm given, which is 69.72. I'm getting that directly from the problem, over 6.022 E23 atoms of Ga. So what I would do then is go ahead and plug that into, again, the on-a-lot calculator. I'm going to clear that out. 1 divided by, well, no, actually, it's not, I'm going to ignore the 1. Let's ignore the 1. So 69.72 divided by 6.022 EE23, and that comes up with our answer. We're expecting something pretty small. Now, as far as sig figs go, we're looking at 4 sig figs. The 1 here doesn't matter for significant figures because it's a counting number. We can't really have half an atom. We can't have 1.5 atoms. We can only have a whole number of atoms, so it's going to be 1. And then this has 4 sig figs on the mass, and the Avogadro's number here, 6.022 times 10 to the 23, has 4 significant figures as well. So the answer here would be 1.158 for rounding times 10 to the negative 22, and it will, of course, will be grams of Ga. Any questions?
How exactly are we gonna type in the E22 onto the blank? Like just normally?
Yeah.
Okay.
Yeah. So let me go ahead and type that in. You type in 1.1, I think it was 1.158, that's what I said. And then E, and then negative 22, and then Ga.
Okay. Thank you.
Yeah, you can't really type it in as an exponent or anything. And if you type it in exactly the way I've got it here, then you'll get full credit for the answer.
All right. Yeah, that's good.
The next one, how many moles of F2? 65.2 liters of F2. All right, so 65.2 liters of F2. Notice how I always put in the units first before I even put in any numbers. So liters of F2 goes on the bottom to cancel, and we're looking for moles of F2 according to the problem, so mole F2. Now the relationship there is 1 mole is 22.414 liters. Again, this is in the relationships that are given to you within the problem. 1 mole, 22.414 liters, and then we do our math on that. I'm not going to do that on the calculator. I know you can handle that. And that's going to be 3 significant figures in our final answer. Any questions?
No, thank you.
The next one. $189.1 grams. And I know this looks complicated. C5, H12, N3O2. It's really just handled pretty much like any of these other problems. Now, this is going to be 2 steps. Now, what we know is that it's going to be G, C5H12, N3O2 on the bottom. And we know we want to finish with atoms of N, because that's what we're looking for, atoms of nitrogen. We know we've got 2 steps because I show you that in the actual problem. So there's no doubt that you actually have to do this in 2 steps. So fill it out that way. What we need is some kind of linking unit here. And the thing is, we can't go directly from grams of C5H12N3O2 to atoms of N. We can't do that in 1 step. So what we do is we need something to link those 2 things together. And what we use is atoms and molecules. So it's going to be molecules of C5H12N3O2 and molecules, because that's the only thing that we have relationships for, C5H12N3O2. The relationship for grams and molecules, according to what we've been given, molecular weight is equal to 6.022 times 10 to the 23. So we've got 6.022 E23 on top, and on the bottom we've got the molecular weight, which is given 146.20. The relationship between atoms of nitrogen and molecules is fairly simple. You can see that in each one molecule, we have 3 atoms of nitrogen. So 3 atoms of N, 1 molecule. So again, we go ahead and we put all that into our calculator. My recommendation would be to do it this way: 189.1 times 6.022 E23 times 3 divided by 146.2. So what we can do is we can always multiply everything on top and divide everything that's on the bottom. So that's what I would put into the calculator, and that should give me the correct answer. Now, making sure, of course, that we're using the on-a-lot calculator properly. Let me see if I can still bring that up. I have to go back and link in new. All right, so clear all that out. So 189.1 times, whoops, clear that, let's try it again. 189.1 times 6 point, no, to clear this out, sorry. 6.022 and then E23 times 3 divided by 146.2. And that should give us our answer. And that would be the answer you'd plug in, but it would be 4 significant figures to match what we started with. So 2.337 times 10 to the 24th, or E24, is what you'd put down as your answer. Okay, any questions?
No.
After we've done question 4, we get on to question 5, which is where we start with the module 8 kinds of questions. So this one, we're given a percentage. And when I'm doing these kinds of problems, I like to, we've got 2 percentages here. What I like to do is do it as a table, and this is the way that I set it up in the soft chalk as well. So N and O, that's where we're starting with. We start off with the percentages, which are going to be 25.9 and 74.1. And what we do is we assume that we have 100 grams of compound. And if we do that, then we end up with the exact same grams as we have as a percentage. The next thing we do is we calculate how many moles of each we have. And we do that by dividing by the atomic mass of the atom. So we've got 14.0. So it would be 1.84 or 1.85 for N. Don't be too concerned about significant figures here, but the way I got that, 1.85 was 25.9 grams of N times 1 mole of N over 14.01 grams of N. That's the atomic mass of N off the periodic table. I do the same thing for oxygen, 74.1 grams of O times 1 mole O over 16.00 grams of O. And I come up with 4.63 moles of oxygen here. Now at this point, we do have a formula. So like N 1.85, O 4.63, but that doesn't really help us very much. What we want here are whole numbers. So the way we can do that is to divide both of these by the smaller of the two. So that's our next step, divide by smallest. And of course, 1.85 divided by 1.85 is 1, and 4.63 divided by 1.85 is 2.50. Okay, so now that is the equivalent of N1O 2.5. But again, we don't want fractions or decimals as part of our formula. So what we have to do is figure out a way to make those whole numbers. And what we can do, since it is a ratio, is we can multiply both of these by 2. And the reason I choose 2 is I'm looking at the 0.5, and my recognition is that 0.5 is equal to, of course, 1/2. So then it would be 2 and 5. So it'd be N2O5 would be my final answer there. The ones that you should know are 0.33 is equal to 1/3, 0.66 is equal to 2/3. So those would be multiplied by 3. And then the other ones, 0.25 is 1/4, and 0.75 is 3/4. And both of those will be multiplied by 4 in the end. So it's not that difficult. You might say, well, gee, I don't want to memorize those. We don't have to. You can always put it in the calculator. And you can say, well, what fraction? You look at what 1/3 is, look at what 2/3 is, and see how close you get to whatever decimal you have. But really, that's how you need to do it. And remember that once you've chosen to multiply something, then you have to multiply both by that same thing. That's what I did here. All right, any questions?
No.
Thank you. Now the next one is about oxides. So it's a similar kind of problem, but we're dealing with an oxide here. Now, what is an oxide? An oxide, according to what we learned in Module 5, is a compound of oxygen. So it is an oxide, and that's the key word there is "ide," or the key suffix is a compound with oxygen. So it is MO. So it's MOXOY. And what we're trying to do here is find these two things here, X and Y. but the whole oxide is MOXOY. So in order to get the oxygen, it's going to be the oxide minus the MO. So it's going to be 6.00 grams minus 4.00 grams. See, it makes sense. The oxide is MOXOY. If we take out the MO, all we're left with is the oxygen. And that would be 2.00 grams of oxygen. This is the step that people kind of forget about the most. So then we go ahead and we do what we need to do here. We do MO, we do O. The number of grams of MO is given in the problem, 4.00 grams. And O is, whoops, is 2.00 grams. The moles, you'd figure out the moles, and then we do exactly, it's pretty much exactly the same as what we just did. So I'm not going to go through the rest of that. The most important step here is figuring out the oxygen by doing a subtraction, and that's what people tend to forget when they're doing this problem. Do you have any questions?
No, no questions.
Now, question 7 could be about figuring out the percentage of water in a hydrate, like this one is. Whoops, sorry about that. Didn't mean to do that. Okay. Or it could just be about finding the percentage of an atom in a compound. So let's do this one here. Again, we're looking at the percentage of water. Let me get out of this. I apologize for this. Sorry about that. The percentage of water is going to be, in this case, 2 times the molecular weight of water, because there's 2 waters in this compound, and then over the molecular weight of the entire thing, which is CaCO3.2H2O. Now, to get that molecular weight, it's going to be Ca plus C plus 3 times O plus 2 times the molecular weight of water. And all of that gets multiplied by 100%. And that's how we get to the percentage. And then it's just multiple choice, figure out which one is closest. Any questions?
Nope.
The next one is about true formulas. And the idea here is we've got NH2, that's the empirical formula. So what I need to do is figure out the empirical weight of that. And the empirical weight is going to be 14 plus 2, which is 16. 14 for the N, and then 1 for each of the hydrogens. The idea here is we're trying to figure out, well, how many of these NH2 units are in the molecular formula, which is 64 grams. So what we do is we take the, well, let's see, we'll do molecular weight divided by, and I'll call this empirical weight because it's the weight of the empirical formula. So I divide them into each other. I've got 64 grams per mole divided by 16 grams per mole, which is going to be 4. So what that means is there's 4 NH2 units. So 4 times NH2 would be N4H8. And that would be the true formula. So I just find that in amongst all of these options, and that would be the answer. Any questions?
Nope.
Once we get to question 9, then we're into module 9, and from there, it's in the home stretch. Now, question 9 is just going to be it's going to be a conversion problem where you have to go from grams or liters to grams or liters. So you need to be prepared for all of those. And after doing this practice test a few times, I think you should be okay with it. I like to use this modified flowchart, and this is what I went through last week in the Zoom session. So if you want more information on this, I recommend you watch my Zoom session from last Friday, which is in the Zoom sessions folder, of course. So the A here can be grams or liters of gas at STP. And B is grams or liters of gas at STP as well. And what we do is we start out here with 150 grams of O2. So we are definitely at here grams of what I'm calling A, which is what we're starting with. Now, whatever's in the flowchart sort of goes along the top here. And you can see how many steps there are. I make it clear in the question. So we'll have moles of A and then moles of B. And what are we looking for? We're looking for liters of H2O. So that's what goes on top here, what I'm looking for, liters of H2O. Now, when I say A, I really should say O2, and for B, I really should say H2O. Sorry about that. Then we know that on the bottom, everything has to cancel. So it'd be moles of O2 on the bottom and then moles of H2O on the bottom down here. And then I can put my relationships in 1 mole, 32.00 grams. I get that from the problem. There it is there. And the relationship between moles of H2O and moles of O2 is from the reaction that we have here. So it'll be 2 moles of H2O and 1 mole of O2. And then the other relationship is 22.414 liters of H2O and 1 mole of H2O. And then we come up with our answer, which of course will be liters of H2O. Do you have any questions?
No.
The next one has to do with what we're calling limiting reagent. So we are given 2 reactants here. You can see them here, C2H2 and Cl2. So Ce2H2, Cl2. These are both reactants, and they're going to give this product here. So remember that the setup is always like this, R goes to P. And in a limiting reagent problem, we're always trying to look at 2 reactants and figure out which one gets used up first. The method goes like this, 5.00 grams C2H2. And you can see there's going to be 2 steps here. And we're starting out with 15.00 grams of Cl2. And again, 2 steps here as well. In the first step, what we're looking for is the moles. So let's go for moles of C2H2 first. And grams of C2H2 will go on the bottom to cancel that. So 1 mole and the molecular weight is 26.04 grams. And that's times 1 over how many moles there are in the reaction equation. In this case, it's just 1 mole of C2H2. So we do exactly the same thing with the Cl2. So moles of Cl2, grams of Cl2, 1 mole and 70.90 grams times 1 over 2 moles of Cl2. So what this will do is it will provide us with two numbers. I'll go ahead and do the calculations here. .192. Now this doesn't have a unit because everything cancels. You see the moles, moles. For the other one, I get 0.106. Now the smaller of these two is the Cl2, so the Cl2 is limiting reagent. The most confusing part of this is this part here, but I'm putting in the square, where we're doing times 1 over the moles in the reaction. Now, that's coming from the reaction, and we're just taking into account the stoichiometry here when we're getting the limiting reagent. So the one that's smaller gives the smaller number, that's going to be the limiting reagent. Times 1 over something is the same as dividing, because like times a half is the same as dividing by 2. Any questions? All right, so I'll do one of these theoretical yield problems, theoretical yield, percent yield. Now, when we're doing this kind of problem, we're, again, it's reactants going to products. And what we want to figure out is how much product, and it's product that we're looking for here, should we get? And that's really the key there, should we get? And that's the theoretical yield. And it's theoretical because we never get everything we want here from a reaction. It's kind of like life, really. So theoretical yield is what we're going to be looking for first. And we're looking for a product, but we're starting with the reactant here. Now the reactant in this instance is, let's see, so we've got 50.0 grams of C. You see C is a reactant. That's what we're going to start with. Now we're looking for, in the end, and what are we looking for? Well, we know that it produces 40 grams of CO, but we know really we should get more than that. And that's what we're trying to figure out. So we're looking for grams of CO. I'm still using my modified flow chart, which I'll put down at the bottom here. So this would be moles of C on top and moles of CO. And then moles of C will go on the bottom here, grams of C will go on the bottom here, and then moles of CO will go over here on the bottom. Then we do our relationships, 1 mole, 12.01 grams of C. And the relationship between moles of CO and moles of C is 2 to 2. So 2 moles of C, 2 moles of CO from the reaction. And then 28.01 grams and 1 mole. Now that's going to come up with a number for us of 16.8 grams. That doesn't seem right. Try that again. Let's try 116.6. That seems more reasonable. But we'll go with 117 grams to match the significant figures, so grams of CO. And you can see that's more than what we actually got, which was 40 grams. So the percent then is going to be actual over theoretical times 100%, which is 40 grams of CO over 117 grams of CO times 100%. And we get from that 34.2%. So we got about a third of what we were expecting out of that reaction. Well, what happened to the rest of it? Well, in any chemical reaction, there's always loss of product. I mean, some of it could have just escaped because we're talking about a gas here with CO, and it just didn't react completely. So we end up getting not the amount we kind of expected or we were hoping to get. We might have been hoping for 100%. We never get 100%, by the way. We try, and in this case, we only got 34.2. Any questions?
No.
Well, that's pretty much all I want to go over. Did you have any questions, Victoria?
No, I don't have any questions.
All right, thank you. Well, we'll leave it there then for today.
Okay.
I appreciate you coming.
Thank
I hope
you.
other people will watch this on video.
Oh, well, thank you for the review.
You're welcome.
Goodbye.
Bye-bye.